how to reverse quantum transformations even if we don't know them.
Thank you. Thank you, the organizers, everyone everyone that is here. It's very good to be back in Brazil. It's been a very good conference. So about this work that I want to talk here today, it's a work that we just finished. There's still some details we're adjusting, so we're still checking what we want to include in this. We have a draft, but it may appear in the archive soon. So it's a work with people that I'm working with in Japan, and the title is, the idea is reversing unknown quantum operations. So I'll basically just kind of warm up to see I'm going to present 3 topics, and if one of these 3 you find interesting, I think there's some possibility that you find this talk interesting. So the idea here would be how can you invert reversible operations in quantum mechanics? And here, we can show that reversible operations in quantum mechanics, they are given by these unitary operations, right? So that would be the big picture. And we're going to have an approach of this higher order operations because we want to do a transformation. And the mathematical methods we're going to explore with these supermaps. And we're also going to discuss this process matrices, this process with indefinite causal order that this week and last week we have several talks on that. And it's quite nice because for us it appears in a very natural way. In the beginning we didn't even consider this process matrix, but they ended up being useful. So here I'll present a few things in the board, but I don't intend to erase anything. So I know that they are recording. Maybe after I can even take a picture if it's useful. So I'll just put here what we would like to do. We would like to just invert one unitary operation. So if you just say like this, you may even ask, well, come on, what you're doing, this is trivial. You can just write a matrix and find the inverse standard algorithms. And moreover, depending on your matrix, for example, the sigma z that we like, if you want to do the inversion, or basically just, you don't need to do anything. It's already inverted. So the main point here is that I want this, I would like to have this in a way that is universal. So that works for every d-dimensional unitary and possibly unknown. I don't want to write a matrix and to invert it. And also before going to the technical details, I think there's a picture that it's very useful to understand. And for me, it's also even a bit personal because it was one of the first things I saw when I started in Japan that has a nice story. This PhD student that showed me that, and then after became a Buddhist monk. And it's been 1 year that he's in a temple in Kyoto, and he told me if there are some results on that, please come in 1 year, because now he cannot have visits. So basically, if you consider, so essentially, that's what he had written to me. So he just showed me this picture and told me well, this is true. So what does it mean here? So this is a general unitary qubit transformation. This is sigma y, the standard sigma y. And actually, if you imagine a circuit like this, you have the complex conjugate of this sigma y. Why the complex conjugate here is this computational basis. And one way to understand this, if you start with a general qubit state here psi, so after this unitary transformation here, the state at this point will be, well, sigma y applied on the state. In this point, you have this unitary sigma y applied to the state, and here sigma y unitary sigma y applied to the state. Then it happens that you can verify it's a straightforward mathematical identity. That this, you may have some global phase, but this is exactly the complex conjugate of the sigma of this qubit unitary. And what is nice about this relation? Because it doesn't matter the qubit unitary you put there. This is true. So this is what I mean by universal. In principle, if you know it's a qubit unitary, you just put it there and you have the complex conjugate. So it's a quite nice and simple way to invert unitary, and it works every time. So this is what I mean by universal. Okay. So if it's SU2, then you don't have this global phase. Actually, this global phase depends on the determinant. If it's SU2, you don't mind. But for us, for practical purpose here, well, the global phase doesn't make a difference for this particular problem, right? Okay. So, and also here, we would like our transformation to be exact. So, like this one, like it's exact, it's not an approximation. And here, it's a good point to reference like other papers on that. We were not the first one to think on this problem. And in this paper here, like quite recently, Kitty Bell and collaborators, they have shown that for this particular task, they have worked for general dimension, not only for qubits. They have shown that you can have like an optimal average fidelity of this 2 over d squared. So for the qubit case, we see this becomes 1/2. So somehow this problem is over, right? At least in the way I phrased in the beginning. Even for qubits, it's not possible. But well, exactly it's not possible. And it's also deterministic is not possible. So we can like abdicate this deterministic aspect and change the problem a little bit by saying that it works some probability. My P is quite weird, but it's supposed to be a P. And then the situation changes a little bit. And actually it becomes possible. So we can do something very similar. And I think for this case, it's useful to see how to implement it. Like if you start with a maximally entangled state and doing a circuit like this and plug here the same constant, sigma y, a general qubit unitary, sigma y again. And here you start with your target state, the state you want to apply the inverse. And here you perform a Bell measurement of these 4 Bell states. You can see that if you click on 5+ here, the state that comes out here, it's exactly the inverse operation. You may also have some global phase that it's not relevant for this particular problem, right? The global phase does not appear. So with some probability that you can actually calculate with P equal to 1/4, this is possible. Okay, so I think it's, well, we started with something quite simple like this, and you can think a little bit, try to be clever. If you see, basically, we are doing like a kind of mixing this teleportation protocol to get the transposition. And okay, but then, well, we would like a bit more, right? This is one example. You can think and try to be clever, think about the circuits. Yes. 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 Maybe I didn't emphasize that, but I would like this probabilistic heralded in the sense that it may fail, but we know when we fail. So, yes, that's what I didn't mention explicitly, but that's what here when you perform this measure, if you get, I know that you click on 5+, and then it works. If it fails, well, I don't mind. Good, good question. So now we would like a bit more. Okay, we work with qubits. There's one example, one probability, but okay, so how, one natural question, is this optimal? Can you increase this success probability in this like heralded scheme? Another like natural question, well, okay, this is qubits, and does it change for general D? And like, how can we increase this success probability? Like, which price can we pay in order to increase this probability? And in order to tackle these questions, well, we can just draw like many circuits, but this is not so nice. It would be good to have like mathematical formalism behind. And for that, we will borrow these concepts of quantum supermaps. And I think it's very useful to recall a few like very standard results in quantum mechanics. Yes. Yes. Yes, actually, we don't do the correction. It happens then. I'm going to talk a bit more on that after, but the thing is, in principle, we can think about doing a correction, similar to teleportation scheme. But in this case, it happens that we don't know how to do this correction, because we are working a framework that we don't know this unitary U. If you have the description of U, it's actually possible to do this correction. Because, yeah. So if it works, it works. If it doesn't work, we cannot correct, at least in this universal unknown paradigm. I don't think so. Maybe it gives like an indirect, maybe it gives like bounds, but non-tight. At least we tried to find, we couldn't find like tight bounds or like non-trivial statements. Maybe there's a way. So these trivial statements I would like to recall that I think they are useful. So in quantum mechanics, so our states, they are linear operators in the d-dimensional space. So here in this talk, I will only stick with finite dimensions to avoid these technicalities of infinite dimension. So how do we transform this state? So which transformations are allowed in quantum mechanics? So we start from this like abstract approach that we say like, we want this transformation to be linear. Well, we have good motivations for that, right? And we also want something like this. If the state is positive, or if you have a positive operator, we want like our maps. So I like to put a tilde to emphasize that this is a super operator, not an operator. We want it to be positive. And this positive operation. And we also require that if the trace of this is 1, this also implies that the trace, the map is 1. And actually, after thinking a little bit about that, right, we also want to ask something a bit more. I'll put this like a 1, like star. That we also want, if you have a state on a larger space, so I put this AB to emphasize, not really Alice and Bob, but we want something like this, right? That if you apply your map into half of the entangled state, potentially entangled state, we also want to be positive. And well, this is the notion of complete positive. I believe well, everyone here knows that, but I would like to keep it for some analogy. And there's something very nice about this approach that connects somehow with this unitary things that usually we learn in initial quantum mechanics books, is that this result known sometimes as Stein-spring dilation, right? And essentially, Stein-spring dilation tells that for any CPTP map, you can write it like this, as a partial trace on some like auxiliary system, where this 0 here is some like auxiliary system. That there exists, you can find a unitary operation that applies on the auxiliary system and your target. Right, and this somehow suggests this picture here. I'll put here your row, your ancilla, and here you trace out. So this is quite nice because there are two ways to approach this general. You can start with like a more concrete way and reach this abstract approach, or you can start with abstract approach and come here. And what about like probabilistic transformations, probabilistic heraldry like that we use in quantum teleportation? Well, they are also simple to do. We just change this partial trace here for a quantum measurement. And then you have this probabilistic thing that will depend on the outcome of this measurement. So now what can we say about these quantum supermaps? Now we want to transform the unitaries, we want to transform the channels, transform transformations. And well, one way to do it, it's in this circuit approach. Very similar to what was done here, right? But here I even accept something a bit more general. So the state comes here, this E stands here for encoder, a general quantum channel, potentially enlarge the subspace for this auxiliary system, and then you apply your input channel, which may be a unitary operation. And then you have this decoder that may involve a partial trace, and if probabilistic, like some quantum measurement. And then this transforms a quantum operation to another one. And it happens that in this paper here, there's a quite nice result that this is essentially the most general thing you can do. So you can ask, what's the most general quantum supermap? So now this analogy here, what would it be? I want like a supermap that transforms CP trace-preserving maps into trace-preserving maps. And I want to transform completely positive into completely positive. And I also want some notion of like a trivial extension, right? If I apply this supermap into half of it, or half into a completely positive map, I also want to preserve this completely positive. And then, as an hypothesis, you can actually prove that the most general supermap has this form. So with theorems like that, there are a few other like characterization results. We can now attack our problem with like a stronger mathematical background. And then we can answer a few questions. For example, is this optimal? Actually, yes, this is indeed the best thing you can do. And qubits are nice, but the qubits, and then something very interesting appears then. For qubits or larger, the probability of success is necessarily 0. So this is very particular for qubits. And now, how can you increase the success probability or deal with this qubits case? Well, one way is to imagine like more copies or more calls. So basically, now we are going to work in regimes like this, so that we have like access to like potentially k calls of this unitary here in a parallel regime or in a sequential that may be better. And then I'll jump now for some like results. So for parallel, we have shown that these probabilities, they are at least as large as this one. And here maybe it's useful writing that this probability of success for this parallel case, asymptotically, I don't know if it's directly, it's like 1 minus 1 over k. If you forget about the dimension, so it approaches to 1. I don't know if it's obvious directly from here, but if you play a bit with this formula, you see that it converges to 1 in this like ratio, this speed. For qubits, or qubits are simpler, we managed to find like the parallel implementation that actually the optimal directly, it's not a bound. And then it happens to be this solution here. And for the sequential case, we can actually perform this measurement, learn a little bit, and do this kind of adaptive that Leandro mentioned. And it's actually considerably better than the parallel case. So for instance, for this sequential case, I don't know if it's possible to see directly there. Maybe I'll put here. You have like something 1 minus 1 over a constant to the k. So then you can see, at least for qubits, you have like an exponential improvement for these sequential protocols. So, well, in the first version of the talk, I had prepared like some technical details here, but then I realized, oh, it's a bit silly. People are interested more technical can talk to me, lunch break or anytime. But maybe it's nice to see how our protocol works for Q-treats. Then maybe you can generalize in your mind. So it's actually very similar to what was done here. But now we start with this Q-treat maximal entangled state. And our encoder will enlarge this space. And the way we do here, like we get this Q-treat and transform into this antisymmetric subspace that has 2 copies. Apply this unitary, and you can show that this is essentially the complex conjugate. And this teleportation-like thing, it's essentially what does the transposition. And then we can discuss the technical details. And something very nice that I'm not going to discuss in this talk, but if you have ever learned about this quantum learning, this is a learning type protocol. So the meaning is that, so this T0, like in time T0, you do that, but so you use your unitaries in a time T0, but the state is required only in time T1. So in principle, you can even play the game. Someone provides you this black box today, and take it back. You use it once. And like 2 days after, they say, now apply the inverse. And you can actually do it. So it's a bonus. It came for free for us. So now, well, in the beginning, I told this very nice story. I said that there is this somehow generalization of Stein spring. But when I moved to many calls, I didn't discuss this subject again. And there is one reason. It's because, well, you can ask the same question. What's the most general supermap that transforms like 2 channels into another one? And maybe you have seen that before, especially in stocks. I don't know with with this language, but this is essentially this process matrices that were, well, it started with this name in this first paper by Chaslev and some collaborators. And if you want more with a closer way to what is presented here, it was actually presented first in this other more recent paper by Mateus and some other collaborators. And well, they have characterized the set of valid supermaps that transform like pairs of channels or like k channels into a single one. And the main point here is that they do not necessarily have this circuit implementation. And because of this indefinite causal order. And we know that the most general transformation may not have this causal order. And are they useful for this particular problem? And now the first interesting thing is that if the number of calls is smaller than d minus 1, actually it's not possible. So the probability of success is 0 if you do this parallel, if you do this sequential, and even with potentially indefinite causal order. So they are not useful. But how about like if you have like more than d minus 1 calls, like can they boost this probability? And well, here, the intuition we had like to construct these protocols didn't really work for indefinite causal order because, well, they're a bit harder to understand. But we can actually tackle this problem with semi-definite programming techniques. So basically, I'll just show something simple here. If you understand something about SDP and these problems, you may understand. But the idea is quite simple. We just want to maximize the success probability such that the supermap transforms unitary D into its inverse with some probability. Oh, I wanted to put tensor K here, sorry. Tensor K, we want that like for every unitary. And this supermap should obey some constraints. And here put some desired set because this SDP works for the parallel, sequential, and also this process matrix. And you just add this as a constraint. And we can put that in the computer and find like the success probabilities. And we present now in this table. So for the qubit case, we can have this parallel, sequential, and definite causal order protocols. Single copy, they are the same. It doesn't make a difference. And the values in blue are the ones we managed to show analytically. And the ones in black, they are results that we got from the computer, like solution as an SDP. And then now here, we can see that indefinite causal order is indeed useful. So, and apparently, it becomes even more useful. So as we have shown that there's an exponential improvement in the parallel and sequential in terms of probability. And here, well, we cannot talk about asymptotic limits because we have like 2 points, right? But we have the feeling that it's large. Okay. And for Q-treats, we didn't manage to go more because the SDP was quite costly. Okay. So now just a few like final remarks. So the main topic was this inversion of unitary invert of unitary transformation in a universal way in this paradigm that you potentially don't know your operation length. And it's possible, but not always. D minus 1 calls are required. And another thing that I think was a nice application of these supermaps because it's one problem that you can see from like a more practical perspective, and the formalism of supermaps is very useful to actually have concrete results. And also, well, in the path of these results, some other general techniques appear, so that like some side results. And an interesting comment, I think, is that it shows that this process matrix, we're still learning how useful they are. They have proven to be useful for like some computational tasks, to improve channel quantum capacity of channels, and a few other things. And now this is one case that they were useful when in one part and not useful in another one. Maybe a nice comment here as well is that perhaps the most famous like process matrix with indefinite causal order is this quantum switch. But for us, the quantum switch is, it seems that it doesn't help, right? Because the unitaries are like the same, and then you may think that you change the order. But oh, it's actually something good to try the quantum switch directly, but okay, we find that. And then for future application is something that we are looking for. So for example, this may be nice if you want to control a quantum system. You want a quantum system that evolves with time, but you don't want it to evolve. Like after some time, you want to apply it inverse, like to prevent time from passing somehow. And this may be used in a protocol like that. There are some papers on that, and we're still trying to understand. And another final comment is like learning type. We didn't explore, but it would. But as I said, it came for free, that in our protocol, the state is required after the unitary. So we still don't know if we can have an application for that. And, well, that's it.
Yeah, great talk. Thank you very much. Other questions?